Hello everyone, and welcome back to What the Heck Math. Today will be the final basic lesson about limits. So far we have been dealing with limits as we approach a certain value, like 4 or -3 or something like that, right? And with those kind of limits, typically in order to solve them, you can just plug that value into its function of whatever limit you're trying to find. Okay, so for example, just as a recap, so if we're going to do the limit as x approaches 2 of x squared, well, what you can do is you can just take this 2 and plug it into x squared, get 2 squared, which is 4. And this is a very simple idea of how to calculate very easy limits when we're just having a certain value and we're plugging in. Now there's one more way that you can look at limits, and this is another useful feature for calculating various things in calculus from here on out, okay? And that is when we're approaching something different than just a number, okay? So for example, let's look at the function 1 over x. Okay, this is a really good example for looking at this idea. So let's just do a quick sketch of 1 over x. So it's going to look something like that. Yeah, close enough. And then something like that. Okay, it's not perfect, but if you want to see a really good image of it, you can use a graphing calculator utility or something like that. But basically, what we're going to look at is what's happening, and you know, maybe I should just draw this again just so we get a better idea of what's going on here. Okay, so let's just try and see if I can be really careful with, oops, that's an accident. Alright, so, alright, okay, good enough. Alright, so what we're going to look at here is what's happening to our y value as our x gets bigger and bigger and bigger and bigger. So we're going to be moving this direction, okay? And we're not going to be approaching 100, a million, or 1,000. We're going to be approaching infinity, okay? So as x is getting this way and getting larger and larger and larger and larger, what's happening to our y value? And you can see, hopefully you know what happens with the 1 over x function. We have what's called a horizontal asymptote. We also have a vertical asymptote, but we're looking at the horizontal asymptote here. So what a horizontal asymptote does is basically it's an invisible line that the function will be approaching but not crossing. So as our x value gets bigger and bigger and bigger and bigger, our y values are getting closer and closer and closer to 0. And that kind of makes sense. If you look at our function here, 1 over a huge number is going to be small. Okay, so 1 over 2, 1 over 4, 1 over 100, 1 over a million. Okay, as that denominator gets bigger and bigger and bigger, the entire number gets smaller and smaller and smaller and approaches 0. So what that basically means is we can say the limit as x approaches infinity of 1 over x is equal to 0. Okay, so this is a really useful thing. So basically, instead of approaching a number like 2 or 4 or -8, we're approaching infinity. And so what this is basically saying is it's showing us what the end behavior of this function is as far as positive infinity. Now, I say positive infinity, so that might make you think, well, what happens when we go to negative infinity? Okay, well, let's look at it. So as our x values are moving this way, approaching negative infinity, you can see, again, we're approaching 0. Now, we're coming from a different direction. We're coming from negative values, but it doesn't make any difference, okay? 0 is still 0. So that means the limit as x approaches negative infinity of 1 over x is also 0. Now, be careful here. These are not one-handed limits, okay? These are one-sided limits. These are both two-sided limits, okay? So don't say, oh, this is the right-sided limit, this is the left-sided limit. Okay, no. Okay, these are both two-sided limits because there's nothing above and to the right of the value. Okay, And in reality, you cannot have a one-sided limit that approaches infinity, because you can't come to infinity from the right. Okay? I mean, what is to the right of infinity? Nothing. It's just more infinity. Okay? So whenever the infinity is this value, it's always going to be technically a two-sided limit. Okay, but you're never going to treat it as a one-sided limit. Okay, so that's the basic idea for limits as they approach infinity. So let's do some different examples. Okay, so let's make it a little bit more complicated here. Let's do some trigonometry. Okay, so we're going to look at this function sine x over x. Okay, and we're going to try and solve this without even knowing what the graph of this function looks like. Okay, because sometimes you can actually work it out if you kind of have an idea of what's going on, and just think about like what makes sense in this problem. Okay, so what we're going to do is we're going to say, all right, we're going to take the limit as x approaches infinity of sim x, apparently. Okay, let's try that again. Sine x, there we go, over x. Now, one thing I want to point out here that I see way too often. I see a lot of students that make the mistake to think, oh, this is a fraction with an x in the top, an x in the bottom. So, because we're division and there's things on the top, numerator and denominator, I can cancel those out, and this just equals sine. This doesn't mean anything in math, okay? In fact, the fact that says sin is kind of evident of what this is. This is a sin. You cannot cancel these things out. You can only cancel these x's out if it's something times x. This is not sine times x. This is sine of x. Just like this is f of x. This is sine of x. X is the input of this function, okay? So just be really careful with... Don't make that mistake, because then it just doesn't make sense. You cannot have sine just by itself with no input. Okay, it doesn't mean anything as far as math's concerned. Okay, now back to what we're talking about. Okay, so again, we want to try and solve this without knowing what this graph looks like. It is helpful to know what the graph looks like, but it's possible to solve without knowing what the graph looks like. So let's think about this, all right? So let's look at one piece at a time. So let's look at the numerator of this function, sine x, okay? So as x gets bigger and bigger and bigger and bigger, what's happening to the output of this function? Well, hopefully you have kind of an idea of what a sine wave looks like. It just oscillates back and forth, back and forth, back and forth, okay? It's never going to be approaching a single value. All right. Now, what values is this function oscillating back and forth between? 1 and negative 1. Okay. So what that's basically saying is, whatever happens as this value gets larger and larger and larger, this numerator is going to always be between 1 and negative 1. Okay. No matter what. Okay. So at most it's going to be equal to 1, and at least it's going to be equal to negative 1. But it's not going to do anything different than that. Doesn't matter how big x is, the output will always be between 1 and negative 1. Okay, so that's what the numerator is doing. Okay, so we could kind of treat this as, all right, so we're going to go, the numerator is going to be between 1 and negative 1, no matter what. Okay, now, what about the denominator? All right, well, like we did before, the example we did before, we were looking at 1 over x, and what was happening to that? Well, x approaches infinity. This thing just gets huge. Okay, so we're going to have a value between negative 1 and 1 over a huge number that's approaching infinity. So essentially, as this is getting closer and closer to infinity, this is having less and less of an impact on the value. So it ends up essentially just being 1 over something huge, which is basically 0. So that means this is equal to 0. Now, if we were approaching negative infinity, same function. again, this is just going to be between -1 and 1. This is going to be something huge, but negative. And again, it's still going to be 0. All right? The answer is still the same. And sometimes you can actually work through limits approaching infinity this way. And this is kind of a shortcut of what's called the Squeeze Theorem in order to solve this. But, you know, there's most of the time with math problems, there's multiple ways to solve the same thing, and this is just one way of solving it. Okay. Now, one thing we haven't covered yet are properties of limits. Okay. And properties of limits basically allow you to simplify the limit so that it's a little bit easier to solve. And I'm actually not really talking about simplifying it like we did with the first video. Okay, simplifying it in a different way. Okay, now these properties of limits actually work regardless of what value you're approaching. Okay, and there's I guess there's really 6 of them. But we're gonna focus on, I don't know, I would say 5, first 5, because they're really the most common ones. Excuse me. Okay, so the first one we have is called the sum rule. Okay, sum meaning addition. Okay, and as I go through these, you're gonna start to possibly just see, oh, okay, this makes sense. I kind of get an idea of what's coming next. All right. So before we're gonna do this, we're gonna say, all right. So let's just say the limit as x approaches positive or negative infinity, okay, either way, doesn't matter, of this function f of x is going to be equal to L, and the limit as x approaches positive or negative infinity of this function g of x is going to be equal to m. So we're just generalizing this, right? So with the sum rule, what the sum rule says is like at the limit as x approaches positive or negative infinity of f of x plus, sum rule, makes sense, plus g of x, okay, is going to be equal to L plus m. Basically what that means is you can split this limit up into 2 individual limits. And sometimes that makes solving it a little easier. Okay. Now this also works if f of x, if one of the functions is just a constant, for example. All right. So just to look at an example, let's say limit as x approaches infinity of 2 plus 1 over x. Okay, so this is a function 2 plus 1 over x. Right. So with the sum rule means that we can split this into 2 limits. So we can say, all right, let's split it into the limit as x approaches infinity of 2 plus the limit as x approaches infinity of 1 over x. Now, this right here, this should be pretty obvious what this is equal to. If it's not, that's okay, all right? So let's think about what this function 2 just looks like if we graphed it, all right? And it's just, so this is the x-axis and y-axis. It's just a horizontal line that doesn't change at y equals 2. So as x gets closer and approaches infinity, what's happening to the y value? Well, it's not changing. It's always going to be 2. So that basically means that this limit right here is equal to 2. Okay. So it's one kind of properties of limits here is that if the function in it is a constant, it doesn't matter what this value is, the answer is going to be that constant. Okay. And we already figured out what this is equal to, 0. So that means this is equal to 2 plus 0, 2. Okay. And that makes a little bit sense if you understand what this is doing to transform this function. It's shifting it up 2 units. So it's moving that horizontal asymptote to y equals 2 instead of y equals 0. Okay. Now, you can also call this sum rule the difference rule. Difference meaning subtraction, because this could be plus or minus. Okay, and it would just change this to a minus, right? So for example, if I change this to that, well, then it's just gonna change this to that, and then it's gonna change this to that, and it's still, this one's still going to be 2, but it's just going to change this plus into a minus. So sum, difference, they work the same way. You can take these polynomial functions or functions with more than one term and split them up into individual limits that are approaching the same value. Okay. Now there's also a product rule. Okay. So using those same limits, I have the limit of f of x is L and g of x is M. Okay. So the product rule, let's write that. Product rule. So we're going to have the limit as x approaches positive or negative infinity of f of x times g of x is going to be equal to L times M. Okay. So another way to look at this is I can take this limit and I can split it up to be the limit as x approaches positive or negative infinity of f of x, all of that, times limit as x approaches positive or negative infinity of g of x. I can split it up into two individual limits that are multiplied by each other, that are approaching the same value. Okay. Now, you can do the same thing with the quotient rule, which is going to be division. Alright? So with the quotient rule, let's go ahead and clear this. It's very similar. The limit as x approaches positive or negative infinity of f of x over g of x is equal to L over M, as long as M is not 0, because when we have a divide by 0 situation, okay, so you can't do that. Okay. And going back to the product rule, if one of these is a constant, just like we did with the sum and difference rule, then it's just a constant here. Okay, so you could just pull that out or move it into the front or something like that. It makes things a little bit easier to solve. Because one good thing about solving limits is if you can take this unknown limit and make it look like a known limit, like 1 over x, sine x over x, something like that, then it gives you the ability to solve it, and it's a lot easier to do so. Okay, let's do a couple of examples before we finish this video. Alright, so let's do the limit as x approaches infinity of 5x plus sine x over x. Okay, so let's solve this. Alright, now, right now, we can have a problem. Okay, so, you can't really plug in infinity, right? Just like if this was a 2 or something, you can't really plug in infinity. You have to kind of look at it as, okay, well, what's happening as the numbers are getting bigger and bigger and bigger? The only problem, this is in kind of a format that we're going to have a huge over a huge, which is like, oh, this is infinity over infinity, which is just going to be 1. Well, that's not always the case, okay? So what's best to do here is to kind of simplify it, using those properties of limits. See if you can rewrite this to look like something else, to make it easier to solve, okay? Let's work on this function and kind of rearrange things to make it look a little bit different, and maybe it'll be easier to solve. Okay, so let's so we have a polynomial in the numerator and a single denominator. All right, so that means we can split up this fraction into two pieces. So I can say that's 5x over x plus sine x over x. Okay, well, here we go. We see 5x divided by x. Those x's cancel out, so we have 5. And sine x over x, we can't change anything there, so we're left with this. And then we have an equivalent limit, which looks like this. Okay, so we've kind of rearranged it a bit. All right, so let's clear this and bring it to the next one. So we're going to say, all right, the limit as x approaches infinity of 5 plus sine x over x. Okay, so now we have the sum rule. We can split this into two limits. Limit as x approaches infinity of 5 plus the limit as x approaches infinity of sine x over x. Well, this is a constant function, so it's just going to be 5 all day long. Doesn't matter what direction we're going and what value we're approaching. Plus, and you remember what the answer for this was? As x goes to infinity, this stays between -1 and 1. This gets huge, which means it's relatively small values over relatively ginormous values, so it's 0. So the answer is 5. Right? That's how you will solve a limit, by using one of those properties. Okay, let's try another one. Let's do a quotient rule one. And you know, it's a little bit of a bigger problem. Okay, but you know, that's gonna be okay. All right, so let's do this. Let's do limit as x approaches infinity. And bear with me while I write this out. All right, I'm not just making this up off the top of my head. I have these prepared, so don't get too impressed. Plus 3x squared minus 5x plus 6. All right, and then all of that divided by 3x to the 4th. All right. Now, if you notice, there's kind of a problem with this one, just like the last one. Okay. So you might think we'll use the quotient rule, okay, which actually could work, but the only problem is, again, we get infinity over infinity. Now, you might be used to the fact where if you have something over itself, that's going to be equal to 1. Well, with limits, that's not necessarily always the case. It could be, but it's not always that way. Okay? So what I think we should do here is the same thing we did to solve the last problem. We can have that over that, minus that over that, plus that over that, minus that over that, plus that over that. Okay? So let's split this up. So we have the limit as x approaches infinity. So we have 3x to the 4th over 3x to the 4th. They're exactly the same, so that's going to be equal to 1. Minus this over this, so it's going to be 2 over 3x plus, so the 3's cancel out, so then we just have 1 over x squared minus 5 over x cubed plus 2 over x to the 4th. Alright, so we split it up into individual ones. Now, these we can split up into individual limits as well. Okay, so instead of writing it all out, because it might take up more screen real estate than I have, and it would just take a bunch of your time, and I don't want to waste your time, let's just kind of quote-unquote distribute this across. So let's do the limit as x approaches infinity of 1. Well, that's going to be 1. Alright, and we're going to subtract the limit as x approaches infinity of this. Well, we have 2 over 3 times infinity, basically. So 2 over something ginormous, which is going to be 0. Alright, limit as x approaches infinity of this. Again, that's going to get huge. 1 over that, 0. Minus limit as x approaches infinity of this. Again, 0. Plus limit as x approaches infinity of this. Again, 0. So the answer is 1 minus 0 plus 0 minus 0 plus 0, 1. Okay. Now, this case, infinity over infinity would be equal to 1. But let's change it a bit so that it won't actually work out that way. And maybe I don't need to actually erase it. Okay. What if I change this to 6? Now, all of a sudden, that first term, even though it's still infinity over infinity, right? But now that first term is 6x to the 4th over 3x squared, which is not 1, it's 2. And then it makes the answer 2 as well. Okay. So, that's probably a good introduction to different limits. There's a lot more problems that you should practice to get better with this, but hopefully this at least gives you a general idea of how limits work so that it can prepare you to move on through your calculus curriculum. Thanks for watching. If you like it, give it a thumbs up. Subscribe if you want to get more videos. And please leave a comment. Feel free to leave a comment if you have any suggestions or anything in particular you want me to cover. And I'll see you next time.